Okay, so hello everyone. My name is Quentin Febvre. I'm a second year PhD student with Ronan, and my supervisors are also Julien Le Sommer and Clément Ebelman in Grenoble. And today I'm going to present you something I've worked on. So it's the joint calibration and mapping of satellite altimetry data using trainable variational models. So I will explain all of this during the presentation. So first, the quantity of interest during this work is the sea surface height. So it's a field that fluctuates, evolves in time, depending on ocean currents, ocean temperature, tides, and things like that. And so this quantity is measured by altimeter satellites that we can see on the left panel, which take a measure at nadir, so vertically below them. So on the center panel, you can see an example of observations for a given day made by 4 satellites. Then those observations are processed by some operational processes, and it produces the map you can see on the right. And this map can then be used for a variety of applications, such as climate monitoring, marine traffic, and stuff. So one thing we can already note is that the observation for a given day have a really high rate of missing value, which can be a challenge for the interpolation task, going from the observation to the dense map. So the problem we address in the work I'm presenting is the fact that there is an upcoming mission which will put a new satellite in orbit with a new kind of sensor. So instead of having a one-dimensional observation, we will have 2 bands of 2-dimensional data, so white swath data that will be acquired. And this new data will come bundled with some spatially correlated errors that we can preview on the panel here. Can you see my mouse pointer or not?
Yes.
Yes, okay. And so, yes, so to visualize the impact of those errors on the quality of the map produced by the operational chains, we have the 4 panel on the right. So on top, without the new observations, we have the nadir observations and the mapping error corresponding. And below, if we add the SWOT observations, we can well see the new topology of observations. But because of the spatially correlated errors, we can see that the mapping error is actually bigger, even though we have more data and with big artifacts. So our objective is to see if we can develop a method to successfully map the new observations and jointly calibrate, provide a calibrated version of the SWOT observations. So for this, we can look at existing approaches for inverse problem. So first, we can look at the variational formulation for inverse problem. So we will estimate the target quantity by finding the state that will minimize a certain variational cost. So we will find a state that minimizes the cost composed of 2 terms, an observation term, which can be traditionally a distance to the observation where we have some observations, and a prior term or regularization term, which is the term that will actually drive the interpolation, in which we will put the a priori knowledge we have about the field. So, for example, it can be a covariance model that we want the target field to comply with, or some dynamics in the form of differential equations that we want the target field also to agree with. And finally, we need to define a way to minimize this variational cost, and this can be done using a gradient descent, so an iterative gradient-based solver in which we iteratively update the state until we have minimized the variational cost. The challenge with this method is that we need to explicitly define a prior, which can be challenging for complex dynamics such as the ocean. And we need to also have an optimization scheme that successfully manages to minimize the prior, which is not trivial at all. Another way to approach this problem is to use deep learning-based, direct learning-based inversion. So we define a parameterized function f with the parameters theta, which will take as input the observation and produce as output the interpolated field. And then we define a training loss on which we will minimize so we will minimize the parameters theta for a given training loss on some data sets that we have. So some key differences is for this, we need to have some training data that we didn't need for the first, for the variational-based inversion. And we need to formulate to the parameterization of f theta. So traditionally, it can be a neural network that we will train. One challenge with this approach is that f theta is kind of a black box algorithm. So if it doesn't work for some reason, it can be difficult to inject some knowledge to improve the results. Yes. And a new approach that has been proposed recently is to combine the two previous methods that we presented, and is to learn a variational inversion scheme, so the 4D Varnet framework. So for this, we still define f theta as a parameterized function that will take as input the observations and produce the interpolated map. But this function f theta will actually minimize a variational cost. And so we can, what we will learn in the training scheme is actually the prior. So instead of explicitly defining a covariance model or some dynamics, the prior will be formulated as a neural network and will be trained on the training data. And we will also train the optimization step that we will perform to minimize the variational cost. So this method has been successfully used for mapping, for the mapping of altimeter data. And in our work, we augment this method for the joint calibration of and mapping of the altimeter data with the uncalibrated SWOT observations. So this is done in two steps. First, we augment the state that we invert by including not only the interpolated map, but also the calibrated observations, so the SWOT observations without the noise. And we also augment the training loss by adding a calibration term that, in order to train the prior and the solver to also generate the calibrated observations. So we will now present the experimental setup. So we demonstrate this approach on simulated geophysical data and errors. So for the pseudo observations, we use the NATL 60 simulation, on which we sample nadir observations from true orbits of nadir satellites, and we sample some the sea surface height acquired by SWOT, given some predicted SWOT orbits. And the experiments are made on the Gulf Stream region, which is a domain 10 degree by 10 degree. Just to visualize the kind of errors we are considering. So these are errors that are simulated by the SWOT simulator. And we have a different kind of error. So what we can see here is the two wide swaths of the SWOT satellite. And we have some errors that are due to some oscillation of the satellite or some instrument errors, or even geophysical error due to the wet troposphere. So finally, the global experimental setup. So we have the NATL simulation from which we sample the SSH of the observations, and we add the errors that are also simulated. So at the bottom, we have the two observations we have, so nadirs and SWOT. And the objective for the calibration task will be to separate the geophysical part from the error part in the SWOT observation. And the mapping objective will be to reconstruct the SSH field, the dense SSH field. So if we first look at the mapping results, so we will compare three approaches. So one is the baseline, so it's the operational chain mentioned before, performed on the calibrated SWOT observations. One is the direct learning approach, so we have a direct CNN that takes the observation and produce the map, and the Febvre cal, which is our proposed approach. We compare these three methods on three metrics. So the mean squared error between the reconstructed map and the ground truth, the mean squared error of the amplitude of the gradients, which you can visualize on the right, and an effective resolution in kilometer, which is a metric computed from the power spectrum densities of the error and ground truth. So some ratio of those two. So first, we can see that the direct learning approach, if we look at the metric, manages to improve slightly the baseline. But when we look at the map, we can see that we have some artifacts and that it isn't quite a plausible geophysical field. And we can see that our proposed methods, so if we look at the metrics, perform significantly better than the other two. And if we look at the map, we can see that some gradients are better reconstructed. And, yes. And something to keep in mind is that if we look at the baseline, it uses the SWOT observations without error. So if we imagine some perfect calibration that has completely eliminated the errors, whereas our approach takes the uncalibrated observation as input. So additionally, of the dense map, we also produce some calibrated observations. So we look at the same three metrics, but computed only on the observed domain by SWOT. And the three value we compare is the uncalibrated SWOT observation, the estimation on the SWOT domain by the operational chain, and the calibrated observation produced by our method. And on the four panels, we can see the ground truth geophysical components and the ground truth error, and what our method estimate for those two components. So one thing we can notice is if we look at the mean squared error, we can see that the calibrated product made by our method eliminates almost 90% of the error, MSE-wise. And another thing to notice is that the estimation locally on the domain observed by SWOT actually outperformed the metrics on the full grid, since we had almost 90 kilometer resolution for the full grid, and here we are 35. And the same thing, we have 50% improvement MSE on the SWOT domain with regard to the total domain. Another result I wanted to present regarding the Febvre was the flexibility of the framework. Since the prior that will drives the inversion is directed by the training loss that we define. We can actually tune the prior by defining a training loss which is compatible with an objective. So here we present the results from two models that have been trained with different losses. So the orange model is the baseline that I've been using so far in the presentation. And the green model is a model that have been trained by putting more importance on the reconstruction of the gradients of the calibrated outputs. And so what we can see a trade-off where the mapping performances see some degradations, but we have, if we look at the calibration performance, almost a 30% improvement in the resolution of the calibrated outputs. And so we can see that if we want to focus, if our focus is to produce good calibrated outputs, we can specify the training loss according to that. Voilà. So some key takeaways about the results of this presentation. So the calibration of upcoming sensors is a challenge for operational mapping schemes, because without them, we saw that the maps produced have actually more errors than without the new data. We presented the 4D VARNet framework, which combines traditional variational inversion schemes with deep learning. And here we applied this framework to the joint calibration and mapping of upcoming wide swath altimeter data, so from the SWOT mission. So something to keep in mind that we demonstrated this approach on simulated data, and that our training scheme was supervised, so we used the supervised training scheme. And we saw that our algorithms produced improved sea surface height maps with comparing it to the baseline or a direct learning inversion scheme, and also produced calibrated observations. Thank you for listening, and I'm available to any questions.
Thanks, Quentin, for the presentation.